So structured file storage versus millions of 3D tiles. Who wins? Does anybody here, by show of hands, have any experience working with 3D data? Okay, quite a lot of you. So I can. My next question would be: if you're working with small scans, small point clouds, few million points, can you please raise your hand? Okay, and somebody working with large scale point clouds? Oh, okay. Can somebody tell me the number of points? Just shout out. What's the size of the point cloud? Do you know approximately? Anybody? 500 million. Okay. Sorry? Billion. Ooh, okay, that's quite large. I want to talk to you and share experiences later. So don't go away. Well, our project was to visualize over 1.3 trillion points in a web browser. So it's 1.3 trillion points all at once in an average user's computer in his web browser. It is quite a challenge. It was, well, it is still quite a challenging task. And the questions we had to ask ourselves was how to render, or let's say serve those points to the client. How will we store the data? And in the end, how will we handle backups and some possible future migrations to other servers? Hi, everybody. My name is Victor. I'm a software engineer, and my colleague who was working with me on this presentation is Mario. I work at the Prometi Prostor company. Mario works at University of Zagreb, Faculty of Geodesy. He was a project lead and quality control for this project. So about this project, the project was to the clicker to do a national LiDAR survey of the whole Croatian territory. So the Croatia, it's not it's not as large. So it is about 56,000 kilometers squared with the area. But for those of you who don't know, the Croatia is neighboring country of Bosnia, and its shape is not maybe as simple. So let's use Blackboard. How do we get the shape of Croatia? You take the letter V, you rotate it, you add a triangle, which is Istria Peninsula. You put about 1,200 different islands. Oh yeah, you split it down here. Um, yeah, and you stretch it in width, height about 450 kilometers, and bada bing, bada boom, you get Croatia. So the shape of Croatia is not as simple, so it's not compact, it's quite irregular in shape. And that was the part that was maybe the difficult, that yeah, that was that made it difficult, not necessarily the area of the country. The specifications of mapping was 4 per square meter in rural areas and 8 points per square meter in urban areas. What we got? We got about 1.3 trillion points. So to put that in perspective, planet Earth has 3 trillion trees. And this is 1.3 is almost the half. So if you counted all the trees in Europe, Asia, and Southern America, you would get about 1.3 trillion. Quite a large number. The density, the math says it's about 20 points per square meter. So it's a bit more than required, but yeah. We got over 62,000 LAZ files, with each file containing, among others, intensity, classification, and number of returns. So thankfully, no RGB coloring. The size of all of that was about 7.55 terabytes. And in the end, one of the main requirements was to provide the framework to manage multiple corrections of parts of the LiDAR point cloud. So we had to come up with a solution to to track changes and, well, to do sort of versioning of the said point cloud. And final product was a WebGIS visualization. Today it looks like this, so you can see that we managed to do this project. On the left, you can see the 2D map. On the right is the 3D. This is a video, so we did manage to visualize the whole of the Croatia all at once. And when you zoom in, you get more and more detailed point cloud. And also, the main thing to mention is that 3D and 2D viewers are connected, so it's not stupid 3D viewers, so they're linked. As you can see, so the map now shows the same area, and it runs quite smoothly on average person's computer. So this was recorded on my MacBook Pro, so it's not some ludicrous specifications of the machine. Okay, we talked what could be the possible solutions to solve this problem. We could use pot3 to render. Pot3 is great. It has really nice visualization of the point cloud. Also, it has really great performance and is tested already on large data sets. But the thing was that it does have a bit smaller community, or, well, uh, at the point that we were deciding which technology to use, the community was a bit smaller, and also it had less frequent releases. The other option for us was to use Cesium. Cesium has a large community. It has once a month updates, and also this clicker doesn't work. And also, it has quite good code readability and extendability, but there is no specialized tools for measuring, changing visualization, coloring, and stuff like that. And also, it needs a lot of customization to get the point cloud to look as good or almost as good as with pot3. The solution we went with was the Cesium, because the thing that we thought about was the most important in that was to have the good support and large community, and these extra specialized tools and visualization can be we manage that by ourselves. A bit more work, but we manage that. To get to Cesium, we needed to process the data. So we have a large data set, as I already said, but the whole territory of Croatia was split in 55 blocks. You can see them here on the whiteboard. And those 55 blocks were then processed individually. We had about 1,100 LAZ files per block. And to get from LAZ to Cesium, we had to convert to PNTS file, and we also decided to compress it in order to save on space. To do the conversion, we used Py3D tile tools, and later on we used 3D tiles tools to merge all of the 55 blocks into a single, let's say, point cloud. So let's talk numbers. How long did it take to process the data? What was the size of all of the PNTS files? What was the average size of the PNTS file? And also, what's the number of all of the PNTS files? It took around 55 days, so it was about 24 hours per block. The complete size was 18 terabytes, where a single PNTS file was around 89, let's say 90 kilobytes. And we got just shy of 200 million PNTS files. 200 million PNTS files. So a lot. What was the obvious solution? How will we handle that? How will we serve it? Well, we have Nginx, we have our client, and we can serve directly those files to our client using Nginx. Problem solved, we can go home, presentation done. No. Wait. So what's the problem with Nginx? We had to think about upcoming annual LiDAR survey. So we handle this one, but next year we will get another one, for 5 years another one, and then another one. So we have to manage all of that data. Also, on that note, in a few years, it is to be expected that we will decide to migrate to a newer server with better performance. So we have to think about that in advance. How will we make our lives easier then? Furthermore, with 200 million files, we have to be careful not to wear out the hard drives because we don't want to change them all of the time. And with a large amount of small files, we have to think about overhead. So let's do a little overhead math. Let's say we have 200 million files and overhead of just optimistically 1 millisecond per file. That's 200 million times 1 millisecond, and we get 200 million milliseconds. When we convert that to hours, we get 55 and a half hours. So that's 2.5 days just for 1 millisecond of overhead. Yep. Okay. And also with that overhead problem, how will we manage our backups? So we have 1 millisecond. It'll be quite hard to reduce that number. Maybe we should focus on reducing the number of 200 million. That could be a bit easier. And then remember that a few years back, we already resolved this problem. So in our web platform, we have 360 panoramas. Those panoramas are, well, per app, we have around, based on the client, we have around 400,000 panoramas, with each panorama being made out of 96 puzzle pieces of small images. So we had that problem with large amount of small files already. And how did we solve it? Well, we decided to package them all up into an SQLite database. So I presume that some of you here will say, okay, this reminds me of GeoPackage or maybe 3D tiles. Yes, we used those formats as an inspiration back then and also as a confirmation that this is a good way to go. So if we package all of our a large amount of tiny files into single files, single database files, we could maybe manage them much easier. So we decided, let's test this out. But let's not stop on SQLite. Let's see if some of the newer technologies can provide maybe better results. I mean, SQLite is quite an old format. So we tested Nginx, SQLite, DuckDB, but DuckDB not as an engine, but their database format, and Apache Parquet. Nginx is great because it's extremely fast, it's simple to configure, it's scalable, it has a low resource usage. But if we use Nginx, it can be hard to manage. We have to work with millions of files, and because of that, we will have extremely slow backups. In other hand, SQLite, we have one file backup. It's easy to use. It's proven solution, as I mentioned before, and also it has low resource usage. On the other hand, it requires us to package the data. Then, if we have some bug or a problem, it's a bit harder than to solve that problem, and we need a service to serve that data. DuckDB uses one file backup, also easy to use, and it is very fast analytical queries, but also we need to package the data, we need a new service, it uses a lot of RAM, and it's not made for file structure. Parquet, similarly, it's one file backup. but it has a large it has a large compression and is great for large data sets. And the con would be the same as DuckDB. So we have to package the data. It needs a new service to serve the data. It takes a lot of RAM, and it's not made for file storage. Let's test our solutions. So in round one, we will test 10 parallel users we will simulate 10 parallel users and measure the throughput. Here are contenders: Nginx, SQLite, DuckDB, and Parquet. Okay, here is the starting line. Hands up, who thinks Nginx will win? Nobody. Okay, who thinks SQLite will win? 1, 2, 3, 4, 5, 6 hands. Great. DuckDB, hands. 1, 2, 3, 4, 5, 6, 7. Okay, DuckDB now is in the lead. Parquet. 1, 2, 3, 4, 5, 6, 7, 8. 8. Okay, Parquet wins. Ready, set, go. Whoa. Oh. And yeah, unfortunately, DuckDB and Parquet didn't even compete as well as we hoped for. And the old technology of SQLite showed us that there is quite a good performance. So we got 408 requests per second throughput. Then I think it's obvious we can eliminate these two solutions and go to the round two, final round, where where Nginx and SQLite fight. Let's go. The file size: 12 terabytes for the SQLite and 18 terabytes for the Nginx. Nginx loses. Number of files: Nginx has just shy of 200 millions, while SQLite has 55 files. So again, Nginx loses. And what was the most important question? What's the duration of the backups of these files? So in the case of SQLite, it was about 5 hours, and in the case of Nginx, 23 days. So Nginx definitely loses. In in our project, I mean, this is not the definite answer for every project, but in our project, we ended up going with SQLite to package all the PNTS files because it had a lot of advantages from backing up, from file size, and the throughput speed. Before I finish, I would like to answer some of the frequently asked questions. The first one: why did we even use DuckDB and Parquet if they're not made for that? Well, the DuckDB and Parquet are new technologies, so we wanted to test if the newer technologies can bring some better performance. And also, to be honest, currently DuckDB and Parquet are quite flashy names, so we wanted to test them to get you to come here to see this presentation. Why didn't we use the COP? Ah, my mouth is right, sorry. This could be a better solution, but in the time when we were planning the whole system, this wasn't an option because it was just in the early stages of the development. Why didn't we just zip the files and then copy them to the backup server and then we're done? Because, as I mentioned before, we needed to track changes and do the versioning because through the time we got changes on the point cloud, but not the whole point cloud, but little bits and pieces scattered around the territory of Croatia. And the last question: why didn't we just use S3 storage and forget about backups because it's done for us? The problem with S3 storage and this sort of file structure is because there are a lot of small files. So when you zoom in, you get a lot of requests, and S3 storage, well, they charge by the request, so it could get quite expensive quite quickly. That's it from me. Thank you very much.